Good morning, everybody. My name is Sunil James, and I'm a product manager with Google Cloud Platform. With me is John Cormie, a senior engineer, also on the team. And today we're going to be introducing to you a brand new feature in Google Compute Engine that delivers to you greater networking control than ever before. So let's get to it. So I know this is supposed to be an advanced session, but I thought it wise to take just a few minutes to walk you through some of the basics of what GCE networking has to offer. So first, Google Compute Engine enables you to create a private Layer 3 network within the context of the broader Google Cloud that can cut across multiple GCE regions. By default, a GCE region is sized to a /16 insider notation, which is about 65,000 RFC 1918 IP addresses. Second, GCE gives you the ability to attach a static public IP address to any given instance within your network. These IPs are portable across zones within a region. Third, as part of the underlying network fabric, GCE delivers to you industrial-grade firewalling technology that enables you to define which incoming connections are accepted by which instances. And by the way, this fabric is the same exact fabric, same global high bandwidth, low latency backbone network that's used by all the other great Google products that you probably use every single day. So we launched GCE last year, and we've spent a lot of time talking to developers, talking to customers, trying to understand what they want to do, what they want to achieve. And from the networking standpoint, it's a long list of things. And we're going to be working very hard to deliver month over month, over the coming months, a great set of networking capabilities. But to start off with for today, I wanted to talk about some of the nearer term or most pressing issues that customers have said they'd like to be able to tackle. First, we've had customers say to us, I'd really like to be able to create and enable hybrid cloud. I'd like to be able to connect my existing data centers with my private GCE network so that I can actually move workloads between two without necessarily breaking the security barrier that exists with my existing WAN. Another use case has been, I'd really like to be able to have the ability to have all my private VMs share just one static IP address. So just give me a NAT opportunity, right? Or give me a NAT instance, for example. And then third, we've had customers who say, I want to be able to instrument proxies within the context of my network so that I could do things like enforce AUP policies and things of that sort. So we've digested all of this feedback, and we're really proud and really excited to give you guys a chance to take a look at the set of advanced routing capabilities that GCE is bringing to market today. So the work that we've done with advanced routing extends upon a set of networking technologies that have been in GCE since day one. The diagram on this slide describes some of the basic components within a GCE network, starting with that red object, which is a massively scalable virtual router that sits at the core of every single GCE network. Every single VM in your network is directly connected to this router. So when a VM needs to send a packet, the router takes a look at the VM's implicit routing table, as indicated by those tan boxes, and then determines what the next hop should be. Starting today, we're beginning to give you a greater ability to actually configure this router than ever before. And that's what GCE Advanced Routing is all about. As you'll see in the rest of this presentation, we've extended the routing capability so that you can do many of the things that I was talking about beforehand and more. But a few procedural items just to make sure we're all on the same page. So first, each cloud project you create includes one routes collection that contains all the routes applicable to the GCE network's provision as part of that project. Second, each GCE network has two default routes, one that automatically routes traffic to the internet and one that routes VM to VM traffic within your network itself. So let's talk about some of the components of what is in GCE Advanced Routing. First off, we have route names. So a route name is the user-friendly name of a route. In this case, we've named the route VPN route to indicate a route for VPN traffic. Second, we have network. Network is the name of the GCE network to which the route is applicable to. Third, we have destination range. This is the set of IP addresses to which the route's going to apply. Fourth, we have instance tags. So instance tags tell the virtual router which VMs a route needs to apply to. So if a route has no tags, for example, it then applies to all the VMs within the network itself. Next hop directs the router to send matching traffic to a designated VM or gateway. Next hop VMs can be identified both by name and by IP address. And then lastly, priority value, which is used to help break ties. Priority value, which is used to help break ties when there are more than one most specific matching route. So lower priority value actually equals higher priority, kind of like when you're prioritizing bugs, if you will. So when a packet leaves a VM, the virtual router employs the following logic to decide how to route the packet itself. First, GCE only keeps the most specific routes that match a packet's destination. Next, it looks at the remaining routes and then only keeps those with the lowest priority value, which, as we mentioned earlier, indicate highest priority. And then lastly, if there are any remaining ties, the virtual router then computes a hash based on the fields you see up on the slide to select the next hop. If a next hop is found, the virtual router then forwards the packet along. If it's not, the virtual router is going to drop that packet and reply back with an ICMP destination or network unreachable error. One last thing I'd like to mention to you is that before you can employ a VM as a forwarding device, you must, upon creating that VM, set the CAN IP forward flag, as shown in the example GCE to command that's on the screen here. The reason for this is because GCE's default security posture prevents VMs from spoofing the source IP address of egressing packets. As such, enabling this flag actually allows the VM to forward packets with the source IP address other than its own, which is exactly the functionality we need here in this case. Now, I know that these capabilities are really powerful, but I know that they're also sometimes really complex. And so, personally, I find it helpful to visualize this kind of stuff. So maybe, John, you can walk us through some examples to kind of describe what we've been having here.
Yeah, thanks, Sunil.
Yeah.
Thank you. All right, so for each one of those things that Sunil just told you about, we're going to illustrate it with an example. The first thing I want to show you an example of is constructing the routing table. All right, so here on the whiteboard, I've drawn a network in Compute Engine, and we have the project's route collection off to the right-hand side there. The components are the route name, 1 through 3, the tags, which I've represented as little tag-shaped colors, and the network, which is the third column. And so the routing table for an instance, remember, is a subset of this project's route collection. And the system constructs it by selecting rows from that table where the network matches and the tags match. You need to know that if there are no tags on a route, it means it matches any VM. So let's look at one example, that top VM there, number 1. It gets route 1 because route 1 has no tags, and so it matches any VM. It gets route 3 because it shares the green tag in common. It does not get route 2 because it doesn't share any tag in common. If you're familiar with Compute Engine firewalls, this is all very similar. All right, now that we have a routing table, imagine a packet leaves the VM, and the system's got to pick the next hop for it. It's going to consult this routing table and walk through that route selection recipe that Sunil just told us about. There are 3 steps, and I'm going to illustrate 2 of those with examples. The first thing the system does, recall, is it's got to pick the most specific routes, the most specific matching routes from the instances table. So for, again, the visual thinkers out there, this is how I think about most specific matches. In this example, we have a packet destined for 10, 120, 1, 2. It's that star at the bottom there. And the routing table is the 4 routes in the upper right corner. First, I want to tell you a little bit about the notation if it's not familiar. For example, 10, 120, 00/16. That's how we denote an IP prefix. The thing on the left-hand side of the slash is the IP prefix, and the thing on the right-hand side tells you how many bits of that address are significant. And so 10, 120, 00/16 means anything that starts with 10.120. All right. Now, I like to think of the IP address space as a giant binary tree. And the root of that tree is the top of that black triangle there. The leaves, all 2 to the 32 of them, are the IP addresses themselves, and they run along the bottom. And the interior nodes are IP prefixes, and that's where we can hang routes off in our table. So there's 4 routes in this example, and you can see visually that for this destination, 3 of them match, black, red, and blue, because our destination lies within the subtrees of those routes. It does not match green because it doesn't lie within the green subtree. Okay, so we have 3 matches, but we only care about the most specific. Now, again, you can see visually that the most specific routes are the smallest subtrees. And so we actually have a tie for most specific between red and blue. Even though black matches, it's less specific than red and blue, and so it doesn't apply. All right, so now we have the most specific matches. The next step of the recipe, the route selection recipe, is the priority selection. That's pretty straightforward. We discard routes of lower priority, so I'm not going to illustrate that. We'll jump to the third step, which is flow hashing. So there can only be one next hop, and so if you have routes, if you have ties left that are equally specific and equal priority, we have to pick one of them somehow. And so as Sunil said earlier, the system computes a hash of the destination packet, and you can see this at the bottom of the slide. H is the hash function, and it operates on all the parts of that packet leaving the VM. The source IP, the source port, if there is one, the destination IP, the destination port, if there is one, and the protocol. And so out of the hash function, we get a number, and we use that number to index into any remaining ties. And whichever route that picks, that's where the packet goes as the next hop. Okay, so now you understand kind of the algorithm, the mechanics of this, but like why? Why do we do this? What is the hash good for? Well, the answer is scale, and I'm going to illustrate it with this example. So in this example network, the administrator has configured it so that all traffic going to the internet needs to pass through a gateway VM, say for some security or policy reason. Now this works fine for a while, but the number of VMs in his or her network is growing over time. And so eventually we get to a point where no one gateway can handle the number of packets that are flowing to the internet. And so yeah, you could buy a bigger VM for the gateway to have more power to process those packets, but eventually you're buying our biggest VM and you can't scale up anymore, you have to scale out. And so you can see in this picture we've scaled out by adding a second gateway. But the second gateway only helps you if you can distribute load across gateways. And so that's where this hash function comes in. What the hash function does is assigns flows to next hops at random. And so as the number of flows grows large, you are distributing your load more or less evenly across gateways. Not perfectly evenly, because every one is kind of a random coin flip. But as the number of flows gets large, it's more or less even. And so that's load balancing of flows leaving the VMs. Now, note that we don't assign packets to gateways randomly. We assign flows randomly. And so that's important because for protocols like TCP, if you're processing packets in parallel, they can get out of order and that slows you down. All right, so we've done a lot of talking about advanced routing. I'm really excited to be able to show it to you today in our demo. What we're going to do is build a site-to-site VPN using Compute Engine, open source software, and the new routing feature. But we're engineers, we're not cowboys or cowgirls. We have to design our network first. So first thing we're gonna do is jump on the whiteboard and sketch out a network design. And it's gonna take a few iterations to get something workable. And I hope those iterations will kind of motivate why routes are important and a good and useful thing. Okay, after we have a design, we're gonna use the GCE util command line tool to show you the routes, or to show you the resources in GCE that have already created to model this network design. Finally, we're going to SSH into VMs, send some packets, and see them moving through our network in the way that we've configured using the traceroute tool and the TCP dump tool. Okay, so first the design phase. Here's an existing hypothetical on-premises back office application that we want to move to the cloud. There's a couple parts. There's the front end here, those Office FE machines. Those are the database clients. And there's the back end, the database itself. All these parts live on a private RFC 1918 real-world network. What I want you to notice about this very simple application is that there's actually 2 layers of security here. The first layer is the application layer. And what I mean by that is those database clients need to have a username and password to log into the database. And that secret credential is embedded in them. Say it's in a config file that's maybe only readable by some user on that box. The second layer of security is the network layer of security. None of these pieces are connected to the public internet, and so if you want to access them, you have to be physically connected to that network. Now notice these two layers are independent and kind of redundant. They back each other up. So if you know the username and password to the database, but you aren't connected to the network, you're out of luck. You can't access the data. And conversely, if you somehow break into the OfficeNet building and connect to the network, but you don't know the username and password, again, you're stuck. So these kind of overlapping or independent, redundant security layers, that's something we're going to try and preserve as we move to the cloud. Now, one constraint, we're not going to move the whole application to the cloud. We're just going to move the front ends. Say, for whatever reason, just to make it interesting, we'll keep Office DB. It has to stay in OfficeNet. All right, so here's our first shot at doing this. Let's be totally naive, just do the simplest thing that could possibly work. We'll take those database clients, spin up VMs for them. Well, first we have to create a network. So we'll create a network, CloudNet, in Compute Engine. We'll take our address space, RFC 1918, it's in the 10 dot range, and we'll split it. We'll give half the address space to the cloud and keep half in OfficeNet. We'll spin up some VMs to represent those database clients, give them public IP addresses, and well, since they need to talk to Office DB, we better put that on the public internet too. And so now, great, everyone can talk to each other, and we're done. Well, no. This is kind of a non-starter for me from a security perspective because we've thrown away our network layer of security. Now anyone at any coffee shop Wi-Fi connection can access our resources over the internet. And so, yeah, we've thrown away that network layer of security. All right, so let's try again and sprinkle some VPN magic on this design and see if that helps us. We'll take Office DB off the public internet, put it back in OfficeNet. That was a bad idea. Let's not do that. Put it back in OfficeNet behind behind the firewall, and but we'll keep those front end VMs on the public network, and we'll spin up VPN tunnels that connect them to the router of OfficeNet. Use say IPsec is your VPN connection. By the way, this is possible without advanced routing. You could have done this a week ago before we launched it. But I see 3 problems with this design that I want to share with you. First problem I see is that if you have n of those front-end VMs, n of those database clients, you need n tunnels. This is more of a remote access scenario than a site-to-site VPN. And so for each of those tunnels, that's an entry in that router's config file. And as the config file grows large with all those tunnels, your network administrator is starting to get sad and grumpy. So that's a problem. N tunnels is a lot to manage. Oh, and moreover, every time you want to scale up or down those VMs in the cloud, which is touted as one of the benefits, you have to go change that config file to add or remove tunnels. It's kind of a management pain. That's the first problem I see. The second problem I see is that those VMs have to have their operating system, their guest OS needs to be specially configured to use the VPN. Their local routing table needs to know which packets go over the VM or the VPN and which packets don't. And so that's a pain to manage because you have a bunch of configurations spread out over all these VMs. Oh, and you need root access to set up those routing tables because it's a privileged operation. So another kind of management pain multiplied by n. The final problem I see with this design is that, well, how do those Cloud FE VMs, those database clients, actually authenticate when they connect to the router? How does the router know that they're allowed to connect to the VPN? Look, there must be some secret key or credential or something also embedded on those Cloud FE VMs that allows them access to that network. And wow, that credential is stored in the exact same place as the application layer credential. And so even though it seems like we have a network layer of security and an application layer of security, they're not really that independent because the secrets are stored in the exact same place. So here's our final design that I want to propose to you guys today. What we're going to do is take the VPN logic and move it out of those client VMs into the network and into a new designated router VM that you can see there, Cloud VPN Gateway on the left. And so he's going to terminate the tunnel that goes to Office Router. And we're going to use GCE routes to direct traffic destined for the VPN to that designated VPN gateway VM. Now this addresses those three problems I claim from the last slide. First of all, now the number of VPN tunnels scales with the number of packets per second that you want to send over it, not the number of users. So you can probably get away with fewer tunnels. The second problem it addresses is that now those client VMs can be totally stock. They don't know anything about the VPN. They can just dump packets on the network, and the network will figure out where they're going based on the destination address. The third problem this addresses is that now the secrets that allow you to authenticate and construct that VPN tunnel live in a different place than the application layer secrets. And so you can also have some policy to back this up and make it even more independent. So say at Office Co, maybe there's one group of developers that work on the application and they have access to the username and password. And they can log into the Cloud FEVM and the database. And maybe there's a separate group of people, the network administrators, that can log into routers. And now Cloud VPN Gateway is one of those routers. And so maybe no one individual has access to both secrets. So this is what I'm going to demo today, and we'll come back to this picture as we go. Great. So during rehearsal, one of our reviewers suggested that, hey, to really model OfficeNet, you should drag a rack full of gear up on stage, servers and routers and everything, and that'll be the physical network that you're going to connect to the cloud. That's great showmanship, but I took the easy way out, and instead of doing that, we're going to create just separate network in GCE that's going to model OfficeNet. So we have two networks in GCE, CloudNet, which is kind of represents the expansion of OfficeNet, which is a second network. And this is actually kind of realistic because two networks in GCE are totally, if they're separate networks, they have no connectivity by default between them. And so it's kind of the same thing. What I want you to note about this slide, or this output of GCE util, is that the two address spaces of the two networks are non-overlapping. And so you can tell the destination network for a packet just by looking at those first two bytes of the address. Okay, I've also created some VMs to model this design. And here they are. We have Cloud FEVM, which, remember, is this guy in the picture. We have two VPN gateways, Cloud VPN Gateway and Office VPN Gateway, that model this guy and this guy. And finally, we have Office DB, which is another VM running over here in OfficeNet. One thing, or two things you can't see here, unfortunately, GCE util doesn't print them, are the tags. Oops. So I've tagged both of these. I've tagged Cloud FEVM and Office DB with the VPN tag, and that's what we're going to use to join routes to them that allow them to use the VPN. And the second thing I've done is I've given, remember the CAN IP forward flag, I've set that on Cloud VPN Gateway and Office VPN Gateway, and that allows them to do their job and forward packets. Okay, so here's what's new, list routes. This is the routes collection for the project, and the defaults aren't that interesting, I haven't changed those. What I want you to notice is these two routes here that make the VPN go, Gateway to Office and Gateway to Cloud. Excuse me. So what this rule says is that if you're a VM on CloudNet and you have the VPN tag, which gives you permission to access the VPN, and you send a packet that falls in this destination range, don't handle it normally. Instead, forward it to this special designated VM for processing, okay? And this address space is the address space of the peer network on the other side of the tunnel. So note the symmetry here. This gateway to cloud is exactly the same in the opposite direction. If you're a VM on OfficeNet and you have the VPN tag and you're sending a packet to CloudNet, then send it to this special VM for processing. Okay, so those are the resources I've created to model this network design. Let's jump on to Cloud FEVM. I'm sorry. Let's jump on to the VPN gateway. Remember, that's this guy right here. And what I want to show you is that I've already installed and configured the Strong Swan VPN software. It's just sudo apt-get install Strong Swan. And I've already set it up so that it's running and the tunnel is established. And you can see that we've joined these two halves of the address space. Okay, so the VPN's up and running. We're going to do a quick connectivity check here. I've now logged into Cloud FEVM. That's this guy. This is our database client. And what we're going to do is send a ping packet, or a ping request to OfficeDB to check connectivity. Now remember that normally, by default, two GCE networks have no connectivity at all. And so the fact that we get a response shows you that something interesting and new and special is happening. The two networks have connectivity to each other. But hey, how do we know that it's really happening in the way that I'm claiming? Well, let's use the traceroute tool to find the path that that packet is taking. And as you can see, it's exactly what we expect from the whiteboard diagram. The first hop is Cloud VPN Gateway. So remember, the ping is going here, first hop. Second hop is the Office VPN Gateway. And third hop is OfficeDB. They're there. Okay, that's pretty cool. Let's jump on to OfficeDB and see what it looks like from the server's perspective. Okay, so I'm going to start a TCP dump. TCP dump is a tool that captures packets that match a certain expression in a Unix machine and print it to the screen. And so I'm going to start that up, and while that's running, I'm going to send that same packet, that same ping request. And so here's what that network flow looks like from the server's perspective. What I think is cool about this dump is that the source address and the destination address are just 10 space, right? You don't see the addresses of the VPN endpoints, and this is why people like VPN. This is why people want VPN, because we took an existing application on one network and we put it on two networks, and the application didn't have to be rewritten or changed in any way, because the packets look exactly the same. And if you've designed your VPN right, you get some of the security benefits too of being on a private network, like confidentiality and authenticity. So that's from the server's perspective. Now, the final thing that I want to show you, I think is the coolest, is a TCP dump from, let me just clear this, from the VPN gateway. So now we're going to capture packets on this guy. I'm going to send that same ping, and we're going to see how this guy handles it. Okay, so wow, there's a lot going on here. I'm going to quickly step through it for you. Oops. Very unlucky there. I captured a packet I didn't want to. Try again. All right. So this very first packet is what's coolest to me. What's cool is that the destination address is on a completely different network than this VM. So like you might, if this is the first time you've seen something like this, you might ask, like, what is this packet doing on my network interface? It's destined for someone else, right? Well, that's the routes collection working. We created a route that said this packet destined for this other guy should go to this Cloud VPN Gateway VM instead. And it is kind of weird to have packets destined for someone else show up on your network interface, but like that's the definition of being a router, right? People dump things on your doorstep, and it's your job to figure out what to do with them next, okay? So, well, what does this VM do with it next? You can see the answer to that in the very next packet. What it does is it encrypts that packet. You can see that. Now it's using the IPsec protocol. It encapsulates it, so the source address is changed to be its own, and the destination address is changed to be the public IP of the other end of the VPN tunnel. And so that's the encapsulation part. It's like an envelope, taking that original packet and putting it in a new, larger packet. You can see it's 132 bytes instead of 64. And sending it to a new destination. Okay, the next time we hear from this flow is a few milliseconds later, and it's actually the ICMP reply coming back. It's coming back from the IP address of the other end of the tunnel. It's also encrypted, it's also encapsulated. So Linux has built-in IPsec support. I've configured it to decrypt, decapsulate that packet, and dump it back on its own local networking stack. And so this next entry shows you that ICMP reply emerging from the tunnel on this Linux machine. Well, I've configured the guest OS, this Linux operating system, to think it's a router. And so it has its own IP forward flag set. And so Linux knows that it has access to this destination network. And so it sends it out for GCE to deliver to the destination, which was actually the original pinger. This last packet is super cool too, because look at the source address, right? This source address is a VM on a totally different network. It's on OfficeNet. And so this is why the CAN IP forward flag is important, because this gateway is actually sending a packet where the source address is not its own. It's like spoofing, right? But it's not for evil, it's for good. It's to create this, it's to make this transparent VPN work. All right, that's everything I wanted to show you in the demo. I hope you guys think this is as cool as I do. I'm going to send it back to Sunil to summarize and wrap this up.
Great. Thank you, John. So as he just said, we just demonstrated to you guys how to move a back office application to the cloud while retaining some of the security properties of it being in a private physical network. Just to recap, we first took the Linux's built-in IPsec stack plus some open source VPN software and GC's advanced routing capability to connect together these two networks at layer 3, so that by specifying GCE routes that directed traffic to the designated gateway VM. Then we set the CAN IP forward flag on that VM acting as the VPN gateway to send forward packets and receive packets for forwarding. And then finally we used traceroute and TCP-dump to show you guys packets flowing from the origin VM through the VPN gateway that was using routes, and then through the VPN tunnel across the public internet, all the while preserving the packet source and destination IP addresses. So now, as you saw, this was just a demo, and it's not meant to be a comprehensive how-to guide to roll your own VPN necessarily. So before you go off and take this demonstration as gospel, I ask you to go talk to security experts at your organization to figure out what makes the most sense for your business. So with that, I'm going to take some questions. If you're thinking about leaving, I'd suggest sticking around for after the questions, because there's one more thing that I'm going to show you after we're done with that. So let me open it up for questions. Yes.
Hi, I was just wondering if it's easily possible. You were showing an example where you have two gateways handling traffic between the cloud environment and the internet, for example. Is it easily possible for one of these gateways to say, I'm serving more traffic than I can handle, I'll spin up another instance of myself somewhere else, and then I either need to reconfigure the routing tables on the router to make that gateway available, or I need to have them pre-configured to just see that new upcoming instance and use it? Like,
yeah, so that's definitely possible. You would have to write the code that does that. So the API to spin up a new instance, it's an API, you can do that. And the API to control the routing table, you can also automate that. So yeah, that's a great idea.
That can be changed on the fly.
Say again, please?
The routing table can be updated on the fly without much latency?
Yes, and so when you create a new route, what happens is it's kind of an async operation. You get back an operation object, and then you can poll that and see when it's complete. And so once it's complete, that means that everyone in the network has got that new route, and it's kind of in service and ready to go.
And that runs in order of milliseconds, or does that take a while?
I think it takes a few seconds right now.
Okay. Mm-hmm.
That's anecdotally.
Thanks.
In a similar interest, so you had your dummy load balancing example, which was just hash-based, simple. Is there a lot of ability in there to actually have it automated and kind of intelligent enough to actually keep track of the amount of flows that are remaining constant to servers and do automatic load balancing that is actually intelligent as the amount of traffic changes on the different servers?
Yeah, so you could do that, but again, you would have to write that automation yourself. So you could have counters on your gateway VMs, monitoring CPU, monitoring how many packets per second they're doing, and react to it by spinning up new instances and then adding routes to add them kind of to the pool of gateways.
Okay, so the servers will actually have to end up giving feedback to the gateway. You can actually have things run, like having the gateway solitarily kind of trying to figure things out.
You can make. From inside GCE, you can make calls to the control API and add new instances and create new routes. So yeah, that's one possible design. Another possible would be to monitor it from the outside and spin up new resources as needed.
Awesome, thank you.
Thank you.
I guess along the same lines, so you said we can do this flow-based load balancing for VPN gateways where my gateways are on a VM. What happens on the north-south traffic where I'm using the public IPs and going out to the world? Do I have that? Will the Google infrastructure essentially take care of spreading my flows or my load across multiple gateways going out to the internet? And I don't have to worry about it, or do I have to do something special myself?
So the answer is that the routing table doesn't know whether it's a VPN connection or an internet gateway. It's just thinking about packets. And so the same trick works in both cases. Does that answer your question, or maybe I didn't understand?
No, I was wondering that to go out to the internet, do I need a separate VM, which is my gateway, and wait,
No,
that's
yeah,
where
so
I'm
this
doing
is
it?
just an option. You don't need to use a separate VM to get to the internet. By default, you get a route, which is, let me actually go back and show
So
you.
it's implicit, right? It's one of the implicit routes that exists within every
Yeah,
single
it's
VM.
an
yeah.
implicit route, but will the implicit route, will whatever that gateway is going to the internet, does that actually load balance across multiple devices from saturating the physical, that whatever device it is?
Well, okay, let me first address the route point. So this default route is what takes you can't see it because I had to truncate to make this fit on the screen, but the next hop is actually an object which is called the default internet gateway. And it's not a real physical thing, it's just something that should be in your mental model. It's the thing that gets you to the internet, and you don't need to worry about scaling it. We worry about that behind the scenes.
Yeah.
And so it's not one physical device. It scales up as needed.
As needed, okay.
And that's part of the magic, so you don't need to worry about that. If you're running your own gateways, though, then as a questioner over there pointed out, yes, you do need to worry about that.
So I realize this demo falls under just one project, but like, given the example you could run, could I use that to establish connectivity between two different projects?
Yes, because from the VPN gateway's perspective, it's just sending packets to an IP address out anywhere on the public internet. So it could be an instance in a different project. It could be an instance running in a different provider's cloud. It could be an instance running in your home data center, and it doesn't matter.
Okay, but in that case, that it would still have to transit to sort of some public IP. Like I couldn't do like, say, I had two different projects. They're all Google Compute projects, but I want to establish connectivity without necessarily hitting outside to make it faster or better.
Okay, you're asking whether it physically leaves the Google infrastructure.
Yeah, maybe it doesn't. Maybe you've handled it. I'm just curious.
Or another way to position is there a short-circuited path from one project to another to get to networks?
Yeah.
So I think the answer, if I'll take a stab at answering this question, there is no short-circuited path. It's still going to egress to whatever egress point that exists at the top of the tree for traffic that's being sent out to the internet. So you do have to have it communicating on a public IP. But that doesn't mean that it's egressing the network. It's just going up to the edge of our network and then right back down.
Oh, okay.
So.
All right, thank you.
So we'll be around to answer a few more questions afterwards, but I want to just take, with 2 minutes left, walk you through one more thing that we're doing. So as I said before, we are part of the cloud networking team at Google Cloud Platform. And so we talked a little bit earlier about all the things that we've heard developers asking for. This is a great starting point, and it's only going to get richer and better in terms of the functionality for just advanced routing. But there are other things that customers are asking for. And so I'm really, really, really excited to talk about load balancing. So we're going to be bringing load balancing as part of the native fabric for Google Compute Engine. We're not releasing details about the service yet. We're building it right now. If you're interested in learning more about load balancing, come up and find me, or go ahead and click on that Google link. I'll leave it up for you guys to write down. It'll take you to a forum that you can answer some questions about what you need out of the service, and I'll follow up with you personally, and we can sit down and talk more about what you need. Additionally, GCE has an early access program whereby you can get access to all the great new upcoming features within Compute Engine, including load balancing when it's available. So that's what we want to say. So thank you very much.
Thank you so much, guys.